Welcome back. In this video we're going to look at Cauchy sequences, and this gives us a way of looking at a sequence and determining whether or not it converges without necessarily knowing what the limit is in advance. So we'll define them in a second, but what we'll show is that these sequences called Cauchy sequences, which basically are sequences where the terms bunch together towards the end of it, are actually exactly the same thing as convergent sequences. So it's going to be really handy in that it gives us a tool for analyzing convergence where we don't have to specify this limit up front. Okay, so here's our definition. We've got a sequence AN and it's called a Cauchy sequence. Essentially, if you go far enough along the sequence, all pairs of terms beyond a certain point are within any specified epsilon. So if we were to read the definition out in full, it says for every epsilon possible, there exists an n, so no matter what choice of epsilon I make, there is a corresponding n, such that for any two terms beyond this point, an and am, the difference between them is less than epsilon. So the intuitive picture here is that our sequence terms are bunching up as the sequence goes on, and after some certain point n, maybe here, then it's guaranteed that no matter which pair of terms I take, the difference between them is less than epsilon. So it doesn't say, notice the difference between this and our convergence definition. In the convergence definition, we had to specify what the limit was that the sequence was converging to. For this definition, all that's required is that the terms themselves get close together as we go far enough across the sequence. So the first thing we're going to do with these things is we're going to prove that every convergent sequence is automatically a Cauchy sequence. Intuitively, this makes sense. We imagine our convergent sequence to have all of the terms clustering around the limit, and it makes sense that these terms will also be close to each other as we go far across the sequence. So we're going to first prove that every convergent sequence is a Cauchy sequence. So we'll start the proof straight off, and we're going to write down a normal template. So to set up, we'll take ourselves a convergent sequence, let xn be a convergent sequence. And we'll just remind ourselves what that will give us. So in our proof, we expect to use the fact that we can make xn minus x as small as we like at some point. And I guess we want to indicate that we're converging to x, so I'll just add that in there. So let xn tend to x, and we'll say that can be our convergent sequence. In fact, it's enough just to write let xn tend to x, and the fact that it's convergent is kind of nicely summarized without having to put too many words down. So that's what we've been given. We now need to show that it's a Cauchy sequence. So we need to show that it fulfills the condition of being a Cauchy sequence, which means that we have to show for every epsilon something is true. So let's define one of those, let epsilon be greater than 0. And let's write down what we're after. We seek n such that if m and n are greater than or equal to n, it follows that the absolute value of xm minus xn is less than epsilon. So that's just restating our Cauchy sequence definition and putting it in the context of this particular problem. Okay, now this one's actually quite straightforward. So if we take absolute value of xm minus xn, which is what we're after, we're going to do our standard trick of introducing the limit inside this absolute value sign here. So it'll be xm, I'll go minus x because that's what I want, and then I'll go plus x and I'll go minus xn. Okay, because you can see that if I introduce this limit like this, then what it's done is it's given me xm minus x and also x minus xn, and these are the kinds of things that we expect to be able to take advantage of and make as small as we like. So let's see how this works back in our proof. So we will choose, in fact, no, let's just keep working in here for the time being. So we can split that up to be less than or equal to absolute value of xm minus x plus absolute value of xn minus x. I'm just going to rearrange the second one just to make it clearer what we're trying to do. Now the key point is here, we can make m and n, xm and xn minus x, as small as we like. So if we make both of those less than epsilon over 2, then overall that whole thing will be less than epsilon, if we can do that. And it turns out we can. We just need to choose an n, our big N, so that these two terms are within epsilon over 2 of x. So maybe we just write down how that works. So choose n such that n being greater than big N implies absolute value of xn minus x is less than epsilon over 2. Okay, and it's going to also follow that if m is also bigger than this n, then xm minus x will also be less than epsilon over 2, and that will give us the result we want. So we're following the usual template. We've let epsilon be greater than 0. We've stated we need to find a value of big N. We've now chosen a value of big N, a particular choice of big N, and now we're going to show that it works. Then, if m and n are both greater than or equal to n, it follows that firstly, xm minus x is less than epsilon over 2, and xn minus x is less than epsilon over 2. Thus, absolute value of xm minus xn, just sort of summarizing our working from the right over there, is going to be less than or equal to absolute value of xm minus x plus absolute value of xn minus x. This is by the triangle inequality, as we just keep coming back to time and time again, which in turn is less than epsilon over 2 plus epsilon over 2, which obviously equals epsilon, and that's that. Okay, now we come to a lemma, and this is that Cauchy sequences are bounded. Now, if you haven't met lemmas before, lemmas and theorems are the same kind of thing. They're both mathematical results that need proving. If you come across a book and you find lemma, all that means is it's going to be a result that's going to be used in a subsequent bigger theorem, probably. So think of a lemma as like a stepping stone theorem towards a larger result. So our expectation here is that we're going to take this lemma and we're going to use it in something else. So our lemma is that Cauchy sequences are bounded. So let's just see if we can develop a little sketch to get some intuition for this. So here's my Cauchy sequence. It's got terms. Here they are. I mean, because we're actually going to prove they're equivalent to convergent sequences, it's hard to draw something that's Cauchy and not convergent, so it's going to look like our convergence thing. So the point of a Cauchy sequence is that if we take a certain value of epsilon and go, so let's say here's epsilon, something or other here. If I've chosen my epsilon, it means if I go beyond n, then any two points are going to, any two sequence terms are going to be within epsilon of each other. So if I want to prove that the Cauchy sequence is bounded, I'm going to make the same argument as I did when I proved that convergent sequences are bounded, just with a slight modification. So first off, we'll notice that we've got finitely many terms here. So we should look at the biggest one of these and keep that in mind as a possibility for our bound. Remember, a bound is just a number so that the entire sequence fits between plus or minus that number. Okay, so what we're going to do is we're going to specify an epsilon, and in fact I'm just going to choose epsilon equals 1. And if I do that, then what it says is that no two terms from n onwards are further than 1 apart from each other. So in particular, if I take my xn, and I go xn plus or minus 1, this will be xn plus 1, xn minus 1, then the fact that it's a Cauchy sequence means that all of the terms following xn must be within 1 of xn itself. So this will be x big N, it should be. So actually, the behavior of the entire right-hand chunk of the sequence is just determined by the size of this xn value plus my 1. Now I could have chosen epsilon equals 0.1, or I could have chosen 1,000,000. Either way, it would have worked just fine. So that's how we're going to go about it. All we need to do is just translate that into slightly more formal language. Okay, so first off, we're going to choose n. No, we should start by saying let xn be a Cauchy sequence. And now we're going to choose n such that if m and n are greater than or equal to it, it follows that the absolute value of xm minus xn is less than 1. So notice I've made a specific choice of epsilon here, taking advantage of the fact that we've been given a Cauchy sequence. It means I'm free to choose a convenient epsilon that's going to work for me, and I'm going to choose the corresponding n. So I chose epsilon equals 1. I'm going to choose the corresponding n so that all my terms beyond that point are less than 1. It also follows that for n greater than or equal to n, absolute value of x big N minus x little n is less than 1. And this implies, if you just double check this working, that the absolute value of the sequence term x little n is less than the absolute value of x big N plus 1. Why did I use the absolute value? Well, if for some reason my limit had been negative, or had been having terms around here, then the thing we actually would want for the sort of bottom end would be xn minus 1, if this were the case. Okay, so I have to, all I'm doing by taking the absolute value argument here is I'm just wrapping these two cases here with a positive xn and a negative xn into the same case, and so I'm just taking the absolute value, adding 1, and that's going to be the bound that I'm after. So the last thing we have to do is provide a bound for the whole sequence, and then we'll be done. So let m be the maximum, because remember, our sequence could have started off like this. It could have had a term up here, right? And it could have been larger than what was happening in the tail of the sequence. So I need to consider everything that comes before my big N. So I put some braces around that. Maximum value of x1, x2, up to xn minus 1. Okay, so, and then I'm going to consider also the absolute value of x big N plus 1. Then m is a bound for the sequence. Okay, so that's interesting. We have found out that Cauchy sequences are bounded. It might pay just to think for a second why we might want to use this. We have now established that a Cauchy sequence is bounded. If you think back to the previous video, the Bolzano-Weierstrass theorem says something about bounded sequences. That's going to let us establish that there actually is a convergent subsequence for any Cauchy sequence. And the limit of that subsequence is going to be useful in producing a proof of what we're actually after, which is the converse of our earlier theorem. And it says that a sequence is convergent if and only if now it's a Cauchy sequence. So the final step is going to be to demonstrate that Cauchy sequences and convergent sequences are actually equivalent to each other. Right, so this leads us to our main result for this video, which is the Cauchy criterion. A sequence converges if and only if it is a Cauchy sequence. So we did the if version already. Did that already done just before. Okay, so a convergent sequence is automatically a Cauchy sequence. We've done that already. So now we have to prove the opposite direction, that if we have a Cauchy sequence, then it is going to also be convergent. So our setup for the proof is going to start by let xn be a Cauchy sequence. Alright, now let's have a think about what we need to produce to actually prove that this sequence converges. We're going to be using the convergence of a sequence definition to show this sequence converges, and we know that that definition requires us to have a limit in advance. So at the moment we don't have a value of a limit, so it's hard to prove that our Cauchy sequence converges because we need to first produce that limit. Okay, so the way we do this is we note that because it's a Cauchy sequence, it's therefore bounded. That was our previous lemma. And because it's a bounded sequence, it has a convergent subsequence. That's the Bolzano-Weierstrass theorem. And that convergent subsequence has a limit, and we're going to let this limit be the limit we'll show that our sequence xn converges to. Okay, so let's write that down. So our sequence xn is bounded. And so by the Bolzano-Weierstrass, I'll just call it BW, it contains a convergent subsequence which we'll call xnk, which converges to x. We will show that this x is the limit of our actual sequence also. Our actual sequence converges to x. Okay, so now we've got all we need to set up our problem. We've got a limit candidate, we've got a Cauchy sequence, and now we're just going to show that this sequence converges. So, as with every sequence we've dealt with so far, to establish it converges to a known limit, we need to start by saying let epsilon be greater than 0. Okay, so xn is Cauchy. Now let's actually, before we do that, let's write down what we're after. We seek n, don't want to break my template, we seek n such that if n is greater than or equal to n, absolute value of xn minus x is less than epsilon. Okay, so here's what we're going to do. We're going to make use of the fact that we have a Cauchy sequence, and we're going to use this limit in the following way. Right, so we know that our subsequence converges, and we know we have a Cauchy sequence. So we're going to start by picking a capital N from the Cauchy sequence definition. So as xn is Cauchy, we'll choose an n such that m and n being greater than n, it follows that the difference between the two terms, xm minus xn, is less than, and again, for reasons we'll see why shortly, I'll choose epsilon over 2. So remember, it's a Cauchy sequence. I'm free to specify epsilon to be as small as I like. I'm going to make epsilon over 2, which because epsilon has already been fixed here. So I'm going to choose epsilon over 2 to be my size I'm after, and this n that I'm choosing corresponds to that. So this is going to be the n that will eventually be this n here also, but we've got a couple of steps to go before we can show that that's the case. Okay, so we also know, we haven't made use of our convergent subsequence yet, so we also know that xnk converges to x, so we better use this too. So choose a term xnk with nk greater than or equal to n. I'm choosing a term from my subsequence whose index in the original sequence is beyond n, so that I can use the Cauchy property on it. And also, I want to make sure it's far enough along that absolute value of x nk minus x is also less than epsilon over 2. Okay, so I'm putting two conditions on this choice of n. That's fine. We've done this double condition thing before. We choose the two n's and then we take the bigger of the two. So I'm choosing my term nk to make sure, using the convergence property to show that xnk minus x is less than epsilon over 2. And then I'm also using the fact that I can keep going and further beyond that if necessary to make sure that the index in the original sequence is beyond n, so that this property, the Cauchy property, is going to apply to it also. Now all we have to do is just do the similar thing to what we did previously. We take the term we want, we turn it into two new ones so we can use the triangle inequality. So I'm going to subtract xnk and add x in k minus x. Now I'll break it up using the triangle inequality. That's less than or equal to x in minus x in k plus absolute value of x in minus x. Alright, so let's see what we've got here. We have this one here, x in minus x in k. This is the Cauchy property. I can make use of that to make that particular piece smaller than epsilon over 2. And then I've also got x in minus x. Well, for this one, I'm going to use the fact that my subsequence converges. There should be a k on there. That should be x in k. Let's get the right color. Alright, so this is x in k minus x. I know that my subsequence converges, so that I'm going to be able to use this piece here to demonstrate that that chunk is also less than epsilon over 2. Okay, so you can see how I'm using both the Cauchy property and the convergence of the subsequence property to make sure that both of these things are going to be less than epsilon over 2. So that is less than epsilon over 2 plus epsilon over 2, which equals epsilon, and we're done. Right, so what we've shown now is that a Cauchy sequence is also a convergent sequence, and a convergent sequence is also a Cauchy sequence. So actually, if we're trying to show a sequence is convergent, we can either use the definition we've been working with so far, or we could just show that it's a Cauchy sequence. They're both equivalent statements for the sequences we're dealing with. So that's really useful. It means that we have a way of proving that a sequence converges that doesn't require us knowing the limit in advance, and that can be really useful. We already had one result of this nature, which was the monotone convergence theorem, but it was very specific. It only worked for monotone sequences that were bounded. Most sequences are probably not going to be monotone, so the Cauchy criterion is a much more general statement that we can use. So we'll catch you next time.